So, as mentioned, the talk today is about zero-shot coordination, and our specific approach is trajectory diversity for zero-shot coordination. This was work done at Facebook AI Research with my collaborators Brandon Kui, Hengyuan Hu, and Jakob Foerster. So the outline for today is that I'm going to introduce zero-shot coordination. I'm going to talk about our approach, which is a mix of population-based training with diversity objective. We're going to dive into the specifics of that trajectory objective. Then I'm going to go over some experiments that hopefully should provide some nice insights, and finish with future work, which should lean nicely into the discussion period. At any point, don't hesitate to stop me if you have questions. Just like interrupt, open a mic, or whatever. That said, let's go. So first of all, what is zero-shot coordination? In the context of collaborative games, zero-shot coordination is a setting for studying AI and how they learn to behave in those cooperative games. The setting is as such. First of all, before the task is even specified, the players have to agree on a training method. How will the policies be produced? Then the players are isolated. The task is revealed. So this is the collaborative environment. In that environment, the players independently train a policy or a joint policy for the task. But then at test time, they're not evaluated according to their own behavior in self-play, so with a policy they train with, but rather by taking one agent from each policy and putting it together in crossplay. So if you look at football, you can have two teams that train together, but at test time, so during a game, they're actually evaluated how they play as a group composed from teammates from the two different teams, independently created. And so this problem is hard because you can never optimize for the crossplay metric directly. You have to do so indirectly because you can never see the agents that you will encounter at test time during training. Is that clear so far? Okay, I assume so.
Yes. Yes.
Thank you. And so why is this even useful? Well, it's a necessary stepping stone towards human-AI coordination. If we have a procedure that produces policies that are not even compatible with each other when run multiple times, what are the odds that those policies could ever cooperate with something as complex as a human? And so the other detail is that we can not always train our AIs on human data because it's either expensive or lacking or simply doesn't cover all possible situations. So we want AIs to be able to generalize to those settings, to be able to cooperate in settings they have never seen before, which is why it's zero shot. And as a simple example, suppose you have AIs that you implement in a self-driving car. You want them to be able to understand things like headlight flashing. So whenever that happens, there's often a message associated to it, but the message depends on the context of the road. Could be a danger, could be a driver, an aggressive driver behind me that tries to pass, could be a speed trap, and so it needs to interpret and react to that accordingly, even though it hasn't maybe not seen that before during training. And so this is a slide I stole from one of Jacob's talks. I just added it in. But essentially, it is to draw the comparison between zero-shot coordination and ad hoc team play. And what he highlights is that the goal of ad hoc team play aims to be a best response to a good pool of policies, but that is often given a priori during training. And so really, it's mostly about a single agent problem because the pool that is given doesn't have to adapt. And so it avoids problems where both agents have to respond to each other and to be collaborative, but from both sides, because issues of coordination can arise from both sides of the pair. And so we take an example from the autoplay for zero-shot coordination paper that introduced the zero-shot setting. And so we look at this lever game. It's a collaborative lever game. Two agents have to select any lever. After their selection, their choices are revealed. And if they selected the same lever, they get a reward associated with that lever. If they select different levers, they get no reward. And so let's take case A to begin with. What would training and self-play achieve here? Well, because all of the levers are equivalent, training in self-play would mean that the two policies will eventually coordinate on selecting any of the possible levers without discrimination. And so that is fine. But if we were to pair them in crossplay, which is what is required on the zero-shot coordination, there's only 1 chance out of 10 that the two agents actually select the same lever. And so the reward is mitigated. In this case, there's nothing we can do, but we have a variation of that in B, where one of the levers is 0.9. And so if we were to do self-play here, it would never select the 0.9 lever. It would still select one of the 1.0 levers because that's what's optimal. You get more reward in self-play. But again, in cross-play, you would end up with an agent that selected any other possible 1.0 levers. But here we actually have a solution that is, for humans, possibly obvious, which is to select the 0.9 because it stands out. And so if we were able to have our agent select the 0.9 lever, they could reliably end up with the same solution that in crossplay actually achieves way higher reward. And so what autoplay does, without going into the details, is that it looks at all the possible symmetries of the environment and requires the agent to be symmetry equivariant. And so in this setting, the symmetries are all of the possible 1.0 levers that can be interchanged. So you interchange both the state, the reward, and the action. And the environment remains essentially the same. The only thing that survives when you impose that symmetry equivariance is the 0.9 lever. And so when training with autoplay, the agents would naturally converge towards selecting the 0.9 lever, which is then the optimal solution for crossplay and zero-shot coordination. Any questions so far?
Hey, Andrea, I have got a question. I have to apologize. I didn't have time to study the paper before the meeting, which is what you try to do. So I'm going to ask some questions now. Can you go back to the slide where you introduce your problem?
Yes. Here we go.
Okay. I was wondering, so players agree on training method. Does that mean let's say you have a team like of 10 guys or something, and they first agree on some sort of training algorithm.
Yes.
And then you disband them. How should I imagine this? So if it's like, how do they then train in isolation from the other guys? It's
okay. So when we say that players agree on a training method, you can think of them as two research labs. So I can have your lab as well as mine at McGill. We both agree on a training method. Say we both agree we will use autoplay, which is a clearly defined method. And so we both agree we'll use autoplay. We're isolated. Now, whoever is running the game will show up and tell us both what the task is. So the task could be, say, the Hanabi collaborative game or any other cooperative task. And now we both independently apply autoplay to train a joint policy. So technically, we both have a full, we train all of the agents required for that setting. So if it's a 3-player setting, we all train like a setting for every, a policy for every player, and we have a full joint policy. But then when we're evaluated in crossplay, we're going to take some of the agents that you trained with some of the agents that I trained. We put them together, maybe by uploading them to a common server, and that's where they are evaluated.
Okay, and so when you say players, I guess you really mean two teams, right? So if it's
yes, sorry.
So for example, two soccer teams agree on a strategy for training their players. Each team has 5 players or something. Then the two teams train just within their local teams, but not against the other teams.
Exactly. Exactly.
And mix them up, basically.
Exactly. You mix them up. So you pick some agents from the first team, some agents from the second team. And importantly, like the teams could never see each other before. And the method was before you even know what the game is. So maybe like you don't even know what the sport is. You just don't have a team of athletes that you need to train for a specific collaborative sport.
So I'm wondering if they're both using the same training method, and presumably they're exposed to the same task and the parameterization and everything is the same.
Yes.
Should there not be a strong expectation that it's likely they will reach the same training outcome?
Well, so this is what we're showing with the lever game. This is what we're showing with the lever game, is that in a setting like this, if you do the naive thing, which is just use self-play, so have whatever RL algorithm, multi-general algorithm you want, just optimize for expected return, it's going to select any of the 1.0 levers. So agent 1 will select, say, like this lever, and at convergence, agent 2 will select the same. But if you run this and I run this on different seeds, well, I might end up selecting this lever. And now, if you pair my agent 1 with your agent 2, they will select different levers. And they get 0 in crossplay. So what we're showing is that, yes, this should, like, we want this to be solved, but in very simple problems, this actually fails. The naive approach of doing self-play, of just optimizing for your return, actually fails in zero-shot coordination in very simple settings. Okay. I'm going to show other examples.
Sometimes very simple settings are good to illustrate this sort of thing, but they don't hold up when you then go into more realistic places, right?
Okay. It also fails in Hanabi, the Hanabi challenge, which is what was studied in the autoplay paper for zero-shot coordination, which is what we study in this paper as well. What the agent, are you familiar with the game Hanabi?
Yeah, I was actually the editor of the journal where Jakob published his paper with the other guys.
Perfect. So for those who don't know, Hanabi is a collaborative card game where you hold the cards backwards, and so the cards are facing the other players who don't know what you have in hand, and players can give hints on your cards, which are from 1 to 5 in 5 different colors, and what you need to do is you need to play the cards to stack them from 1 to 5 in 5 different colors. What will happen if you do just self-play is that the agents will learn to use very weird hints, such as if I hint that your second card is red, it means that you have to play your fifth, and so on. And if I hint that your third card is blue, it means you have to discard your first. But if you think about it, the colors, there's a symmetry with respect to the colors. And so you could have any permutation of the colors and obtain an equally valid code that is very hacky, but that works in self-play. And so if you do this, if you just do self-play in Hanabi, you obtain policies with very weird behaviors, very weird forms of communication that just are not reproducible. And you get a way lower score in crossplay than you do in self-play. And I'm going to go over all of this as well, because we have experiments in Hanabi as well. So this is a real problem that occurs at almost any level, so including toy settings, including something as heavy as Hanabi.
I wouldn't say Hanabi is. I wouldn't exactly say that it's a compelling real-world example. It's very heavily conditioned by strict structure. I was looking more. So you brought up autonomous driving, right? Autonomous driving is an interesting thing. A lot of labs in the recent years using this as examples, even though they've never worked in this space. Can you give me an example in autonomous driving, for example? You brought up this indication thing, but I don't find that very compelling because there's lots of reasons for why I can interpret someone else's indicator that are outside my own training regime.
Well, but you would have to interpret it and react accordingly in a zero-shot fashion. That was mostly to illustrate like why zero-shot is necessary. But so headlight flashing still, you could possibly not encounter a scenario where someone warns you about a speed trap, right? It could be that all you've encountered during training is that an agent flashes you to maybe warn you about a hazard on the road, but never about speed traps. And so now how you will react might not be in line with what they're actually trying to communicate to you. And this is kind of the same idea as in Hanabi, where someone hints, like if you train those self-play policies and they hint blue, you might believe, oh, it actually means they want me to play the card, but because of their own weird behavior, it means they wanted you to discard.
Okay, I'll let you go on with the presentation. I've already used up too much of your time, but thanks for explaining. Thank you.
No worries. And like, if you have other questions, please don't hesitate. We can also discuss more at the discussion period. So going back, we covered autoplay. The issue is that it actually requires knowledge of the symmetries. And moreover, it requires the symmetries to even be present in the first place. And so we take a second example, which is this corridor game. And you have two robots, A and B, that have to reach the same end of the corridor. If they do, they get rewarded plus 10. If they don't in a given limit of time, they actually get a reward of 0. And so what happens is that A moves first. B can move at the same time, but it can also decide to wait and see in which direction A went. And so in the first example, the setting is symmetric. So you have plus 10 on both sides. It looks symmetric. So autoplay would actually work. In the second setting, autoplay no longer works because we have stochasticity on the left, so either plus 11 or plus 9 with still an expectation of plus 10, and deterministically you get plus 10 reward on the right. And so we no longer have symmetry in the rewards. Autoplay just doesn't apply anymore in this case. Similarly, if we have a kink in the corridor, the transitions required to reach the reward are no longer the same. So again, symmetry is broken and autoplay doesn't work. And so we want something that will work in this setting and learn the optimal zero-shot policy, which, to be clear, means that A moves first and B waits to see that movement. And once it saw in which direction A is going, it just starts to follow. And so our approach is a mix of population-based training and diversity, what we call trajectory diversity later on. And so as a reminder, we cannot directly optimize for crossplay, so we need a different approach. And specifically, we want an approach that will cover the blind spots of autoplay. Our solution to that is that we train n joint policies that we want them to be diverse. So we train them in self-play, indicated by the gray arrows, but we also want them to be diverse from each other, so have different behaviors, as indicated by the dotted blue arrows. On top of that, we train a common best response that will train to be good with all of the policies below, and vice versa, all of the policies will actually be encouraged to be good with the common best response. So if you look at the loss for the entire population, including the best response policy, we want to essentially maximize the sum of the expected return of the best response with the individual policies, of the expected return of the individual policies in self-play, the expected return of the best response in self-play, as well as some diversity objective, with alpha for just a weight scaling. And so the question is, what is the diversity objective? But first, let me give you some intuitions for our approach. There are two main points that are driving our approach. The first one is that if we have a population that represents a diverse set of behaviors, training a best response to them will actually robustify the best response. And so it's more likely to, first of all, behave well when off distribution. And also it's more likely that whatever it encounters in zero shot might have been covered, at least partially, by the population it was trained to. But there's a second effect, and that is that we assume that diverse sets of policies with a common best response are rare in the setting. So if you think about it, there's a lot of different self-play policies that use really weird behavior, really weird encryptic behavior, but that are still optimal in self-play. And any permutation of that is actually still optimal in self-play. So you have a lot of those individual policies, but you have very few, or the assumption that we have fewer policies that are distinct from each other, but that share a common best response. And so if we're able to have or to find those sets of policies that share a common best response, and we are able to compute that best response, we're most likely to have a repeatable process, such that if we do this entire process a second time, or if like another team of researchers does the same process, they're likely to find the same set of diverse policies with the same best response, and therefore we end up with similar, if not identical, policies. This is the intuition behind our approach. And so it facilitates the equilibrium selection inherent to zero-shot coordination. And so this brings us to what is the diversity objective, and we call this trajectory diversity for a reason that's going to be obvious in just a second. Generally, before that, any question on the generic setting, on the PBT setup? I'll take that as a no. So what is a trajectory or diversity objective? I call it trajectory diversity. Generally, in multi-agent RL, we know that agents act based on action observation histories, or in this case, well, which would denote tau t, so truncated trajectories. Furthermore, a joint policy pi induces a distribution over the trajectories. We can decompose that distribution, so the probability of tau given pi, with pi of tau and epsilon of tau. Here, epsilon of tau captures the transition probabilities inherent to the environment, and pi of tau is just the product of all action probabilities. And so if we decompose this further, epsilon of tau becomes the first term here, so the probability of the initial state, times the product of the probability of every single transition we saw along that trajectory. And this is multiplied with pi of tau, which is the product of all action probabilities taken along that trajectory. And so, in short, this distribution fully characterizes the policy. So if you're able to specify the exact distribution of a policy, and if I know exactly the transition dynamics, I could compute all of the pi, the action probabilities, which means I could specify an entire policy that way. And so what that means is that two policies can be said to be different if they induce different trajectory distributions. And vice versa, we can use those trajectory distributions to measure diversity. And so this is exactly what we're going to do. Because those are distributions, we can use any form of probability divergence that we want. In our case, we chose the Jensen-Shannon divergence, which has some nice properties, which was also used in GANs. So we define the average distribution, which is pi hat. And it's essentially just sampling one of the policies from population at the first step and then rolling it to the end. And if we do that procedure, it creates a different distribution, which is what we call the average distribution. And so having that, we're equipped to compute the Jensen-Shannon divergence over the trajectory distributions over population. And so the definition of the Jensen-Shannon divergence over n terms is simply the entropy of the average distribution minus the average of the entropy of individual distributions. And if you rearrange that, it's actually equivalent to the average KL divergence from each individual distribution from the average. So one way you can see it is that we want the average, meaning the set of behaviors of all or policies, to cover as much of the trajectory space as possible, which is why we maximize for the average entropy, or the entropy of the average. But at the same time, we want all of the individual policies to have as small of an entropy as possible in order to maximize this term. And so what that means is that essentially you want them to cover disjoint parts of the trajectory space as much as possible, because this is the only way you can maximize this term. Another way of seeing this is with the KL term. And so every policy is trying to be as different from the average as possible. This has some nice properties, as I mentioned. So the Jensen-Shannon divergence is permutation invariant. So you can swap the policies around without affecting the term, which is not something you get with just doing the KL divergence. It's generalizable to any arbitrary number of policies, which is also nice because you don't have to do it pairwise. It's also bounded between 0 and log n, which is nice for interpretability, and it avoids having something that explodes in the extremes. And a small fact for n equals 2, the square root of the Jensen-Shannon divergence is a proper metric, which gives some intuition that we actually induce some form of real distance between the individual policies. So before I carry on with an example, any questions so far? I'm going to have an example to show how this works in just a minute.
No, you can go forward.
OK, perfect. So taking back the corridor example we had from before, what I want to see is that, just to give an intuition, how this is actually maximized. So suppose we have a first joint policy that always goes left. And in our population, we have a second joint policy that always goes right. If we compute the Jensen-Shannon divergence, well, pi hat, the average policy, will go 50% of the time left, 50% of the time right. And so the entropy of that is log 2. And if you take afterwards 0.5 times the entropy of every individual policy, well, every individual policy is deterministic. So its own entropy is going to be 0. And so we get log 2 minus 0, which is 1. But log 2 is what we mentioned before as our bound. And so it means that in this setting, and this holds in general, if we have deterministic policies that are disjoint, we actually maximize this objective. What is interesting, though, is that we don't actually need to have deterministic policies, despite the fact that we are minimizing the term here. So we're minimizing the entropy of individual policies. We don't need them to be fully deterministic. We actually can afford any amount of entropy as long as they are disjoint. And so really what we are pushing for is that we want disjoint sets. We want the support of the trajectory distributions to be disjoint. And so that is all nice, but beyond simple settings, we actually have a problem. And that is that the Jensen-Shannon divergence looks at global differences. Any two trajectories, as long as they have a small action difference, will be considered as entirely different trajectories for the purpose of the Jensen-Shannon divergence. And so in that sense, it's too sensitive and easy to saturate, because agents can decide that they're going to follow the exact same path and at the end just have a small action difference where it doesn't matter. And that will be considered different. Another way of seeing this is that the longer your trajectories, because you have action probabilities, the longer, the more are the odds of two agents just naturally diverging, even though we don't actually try to optimize for diversity, just from the nature of the objective. And so we need something else that considers local differences. We need something that we can tune in terms of how sensitive we want it to be. And we do this with action discounting, and specifically an exponential kernel over time steps. So before, we had the trajectory distributions defined here, as well as the average trajectory distribution. And we replace this by an exponential kernel at time step t and the average of overall the kernels. So just to break this down, it looks scary, but if you take the if you were to take the log, break it down, it's actually not that different from how reward discounting is working in regular RL. The only difference is that here we are looking both in the past and in the future. And so if you take a time step t, we'll look at the action probability for that time step, multiplied with the action probabilities in the future and in the past, but discounted with this exponential discounting such that actions taken far away will basically have a term equal to 1 and won't matter in the product. A different way of seeing it, and we have some experiments with that, is that you could have a windowed kernel, where just like you consider the past 3 steps and the future 3 steps, and with the current one, that would be a total of 7 time steps, and then just look at the action probabilities for the 7 time steps, forgetting what happened in the past, like before and after that. And so with this kernel, we can actually control how much sensitivity we want, whether we want global diversity at the level of trajectories in the extreme, or we want to look at individual differences at individual actions at the other extreme, or anywhere in between. And so if we take our Jensen-Shannon divergence from before, we replace the terms with those exponential kernels, we obtain our TrajeDi objective, which is a discounted Jensen-Shannon divergence. Any questions? I guess not. So this is what we'll use for our experiments quickly. The first experiment is, again, just a simple toy setting to provide some insight. We have this collaborative matrix game. So there's a row player and a column player. They both select an action, either a row or a column, and the intersection of the two is revealed, and that gives them both the reward, which is the same for both agents because this is a collaborative setting, as I mentioned. So what happens if we train in green individual agents, in orange a population of 2 agents, but without diversity and with the best response on top, and we only evaluate the best response. And finally, we have a population of 2 agents that are pushed to be diverse with TrajeDi and with the best response on top. And so in self-play, they all perform great. So they all successfully reach agree on one of the cells that give 1 reward. But in crossplay, we see that both individual agents and a best response to a non-diverse population actually perform the same and close to random. Meanwhile, the best response to a diverse population maintains its score both in self-play and crossplay. And why is that? Because the only way you can have 2 diverse agents with a common best response is that if you have one agent selecting the first row, the other agent selecting the second row, and then the best response would be the column here. You might remember that we want diversity in the joint policies, and so this works because you would select either 0, 0 or 0, 1. And so this is exactly an example of diversity being used to facilitate finding the equilibrium of the setting, which is what I mentioned before. A second example, quickly, is from actually single agent RL. And this is just looking at how the construction of an MDP can actually influence the reachability of different solutions, whereas they're all equally valid. So here we have no discount factor on the reward. And so every one of the green leaves of this tree-like environment provides a reward of 1, and the other ones don't provide any reward. And so if you train a population, we're curious to see how likely are we to find all solutions of this environment. And what we do is we have a baseline population, so no diversity, as well as a diverse population. And we'll look at both random initialization and entropic initialization to see what are the odds. Entropic initialization just means that all of the trajectories are equally likely, which in this case we hard code, but in a large setting could do with something like max and RL. And in the first setting, what we see is that the baseline population, whether randomly or entropically initialized, actually prefers the first two solutions way more. And it's not hard to see why. It's just because at any point, you actually have a larger reward density on the left than on the right. And so this will bias the policies to go in that direction. Meanwhile, with TrajeDi, so with diversity, we actually succeed in finding all of the four, well, we more reliably find all four solutions. And if you add entropic initialization on top, we actually find them all on every single iteration of this process. The same thing holds in this very unbalanced tree, where you have very easily reachable solutions and very hardly reachable solutions. And again, the baseline population will most often just find the first two solutions. Even the second one actually is very unlikely, so mostly the first one. Whereas with TrajeDi, we start finding more and more. And with entropic initialization, we actually find them all reliably. And finally, I promised you Hanabi results. And so in Hanabi, what we did is we had a population of 3 agents with a common best response. We mixed TrajeDi with autoplay and an auxiliary task. The auxiliary task is just predicting if every card is playable, discardable, or unknown, which is also something that they used in the autoplay paper. And the reason we can combine the two is because TrajeDi and autoplay actually address very different aspects of zero-shot coordination. And there's one caveat here where we hit the last action. So the agents don't see what was the last action done by the agents before. The reason we do this is because it reduces the probability that they actually use that to communicate. And so it simplifies a bit the setting for our purposes. We believe that if we increase n with enough compute, we actually no longer need this requirement, but this is not something we've tested yet. And so looking quickly at the results, we have a single autoplay agent that achieves 24.24 in self-play, 22.65 in cross-play. If you have a pool of those agents with the best response, we perform no different. In fact, self-play is actually a bit lower. Jumping a row, if we have the same pool with the best response, but now the pool is actually encouraged to have TrajeDi on top, we achieve almost identical self-play, but our cross-play is increased by a large margin. And now going back, what's interesting is that if we have a best response to a pool, but we slow down the pool, so we actually perform the TrajeDi computation, but don't propagate the gradient for TrajeDi, we again gain some level of crossplay improvement over just the vanilla pool, but not as much as if we had diversity. So what that tells us is that some of the gain is actually coming from slowing down the pool that we respond to. And we believe that this is because the best response will see more of those early stage behaviors, and in turn will robustify it more or act as a regularizer on the policy that it learns. And finally, we tried, as I mentioned before, with a windowed kernel, and we also get some gains, just not as much as with the exponential one. And so there's a range of future work that we can do, which is improve some of the Hanabi results and not use the observation hacking of the last action, implement this in other settings, such as grid words and overcooked, also SMAC. And finally, extend to semantic diversity and maybe combine it with something like off-belief learning, which was another ICML paper. And what I mean by semantic diversity is that TrajeDi, although it does improve the crossplay scores, wasn't able to produce very understandable and clear diversity in Hanabi. And so we are looking at ways of actually making that happen, of like learning drastically different conventions and behaviors. Thank you. And I guess now's the time for questions and discussion.